Good morning. I am Krishnamar from Krishna's Classroom. Welcome to you all. Well, we continue with our lectures on the structure of linear transformations on R. In fact, in this talk, what I want to present before you is the beautiful inner structure that you see on Lx, where X is an n-dimensional vector space over R. Of course, as I said, in a more general scenario, you can say that X is a linear space over a field Rn, because over a field over a field R. Okay, so that is possible. Now we are interested only in Rn for the time being, because our eventual objective is to talk about functions defined from Rn to Rn. Okay, but let us explore this a bit. Now, you see that, so I am interested in T belonging to Lx. So T is a linear transformation on X. So X I am taking dimension of X equal to n, and the associated field is X is a linear space over R. So this is the basic premises that I take upon. Okay. Now we have already seen that if I choose an ordered basis for X, then I get an isomorphism of X onto R. Conversely, if there is an isomorphism of X onto Rn, then it determines a ordered basis, and the ordered basis corresponds to the isomorphism. Okay, so the two things are synonymous. So what I have is the following picture. So I have X here. Okay, then I have a copy of Rn obtained by choosing an ordered basis x1, x2, etc., xn. What I then have is, if I start with an x belonging to X, X gets mapped to, say, call this B. I can call this phi B, the isomorphism. So let alpha, where alpha is equal to alpha 1, alpha 2, etc., alpha n, and the connection is that X is equal to alpha 1 x1 plus, where x1, x2, etc., xn is an ordered basis. Okay, so this is the identification that I have. So alpha is a column vector. Okay, so this is a 1 into n rows and 1 column. So it is n into 1 matrix that I have. Now what I said was that this representation is essentially depend on the choice of the ordered basis. If I change the ordered basis, then I get another representation because these coefficients are going to differ. That's the reason. Okay, right. Now this is what we have already. Now what I want to explore is the following. I want to look at linear operators on X. I gave a general scenario of a map from an n-dimensional space to an m-dimensional space, and then we got the matrix representation, etc. I am going to do this for the specific case from X to X. So it may appear to be a bit repetitive, but okay. So what I have is the following. I have X, I make another copy of X. We fix the basis, ordered basis. So I have an ordered basis. So this is the ordered basis I have. Now you see that once I fix the ordered basis, I have a copy of Rn. So I make two copies of Rn. I start with an X here. I have the linear transformation T belonging to Lx. So it carries this to the vector Tx. Okay. So this is the domain space, this is the range space. I have separated one. It's actually from X to X. Okay. Now what I have is, this has a unique column vector corresponding to it. Once you fix B, now this is denoted by alpha. As I explained that. Now Tx is again a vector in X. Now let this be denoted by some beta, where Tx is equal to, so what I have is that X is Tx therefore Tx is identified by beta 1, beta a, the column vector beta a. Now you see that, how is this beta obtained? Okay, let us work it out. So you see that this is what we had, that we computed Txj equal to, it's a linear combination of x1, x2, etc. xn. So this I write as sigma I equal to 1 to n alpha ij xn, or let me write here, I don't want to use aij xn. Okay, this is for I running, j running from now you can write down Tx is beta 1 x1 plus beta 2 x2 etc. beta n xn. Okay. At the same time, Tx is also equal to alpha 1 Tx1 Txn, T being linear. Now each Txi you can replace or tx1 you can replace by the corresponding expression with j equal to 1, etc., etc. So you get this, and eventually what you see that you see that this is equal to, this corresponds to alpha being, there is a n by n matrix A which you want to denote by Aij, and such that you can write beta equal to A alpha. Okay, or more explicitly I can write this in this way: beta 1, beta 2, etc., beta n, this column vector as the map of or image of alpha 1, alpha 2, etc. under the corresponding to the multiplication by the matrix A11, A1n, An1. So the typical number is Aij. Typical number. This is actually the ith row. Okay, right? So this is the matrix representation that you obtain. This we have discussed in the more general scenarios. You work it out. So this is exactly, means just as that of putting in this inside this and then comparing. So this is, this side it is going to be beta 1 x1 plus etc. beta n xn. On this side you collect coefficients of x1, x2, etc., and then you weight, and then you get this kind of representation. So you can use the matrix theory to write this in this particular form. This is what we have. Okay, fine. So this is now represented by a matrix. So A maps alpha to beta, beta equal to A alpha. This is the picture that you get in that. So for every operator T on X, once you fix your ordered basis, there is a matrix representation, and the entire operation of mapping by T of a vector can be conceived as multiplication by A of the representative of X in R. Okay, so this is the scenario that comes up, and this I denote by phi B, and this is also I am using the same B. I don't want to change the basis in which the representation takes place. Okay, fine. So last time I just computed this. So this is equal to A is essentially equal to phi B inverse T phi. That is, this map can be thought of going backward from alpha to x, x to tx, and tx to beta. Okay, so this is the connection that you have. This is the beautiful picture that emerges out of it. Okay. Therefore, you see that the representation of T corresponds to a getting an isomorphism of X to Rn. Okay. So your natural question that you ask is, suppose you change the order basis, which means you change the isomorphism. Once you change the isomorphism, what happens? Naturally, you expect a new matrix representation to emerge. Okay, so let us explore how these things work. Okay, so let me draw another picture, and these schematic diagrams tell you everything about all of this. So you have X here, X here. You have a copy of Rn. You have another copy of Rn. Same copy of Rn, in fact. Now this is through an isomorphism phi b. Now the corresponding. Suppose this is X. X is mapped to Tx. And this goes to alpha. This is now identified as A alpha. And A is equal to T. Let me just put it this way. So order basis. Or I can write as A of T of phi b. Right. What are the other possibilities? Suppose I choose another order basis. Okay. Then I get another copy of R. Okay. So what do I get? I get I introduce another ordered basis. Say, let me introduce a new ordered basis, B prime, which we define as ordered basis y1, y2, etc. yn. So I have now an isomorphism phi b prime. Let us denote the representation of X under this choice of ordered basis, or the image of X under the isomorphism phi b prime to be gamma. So let me take gamma to be equal to, so what is gamma? Gamma is gamma 1, gamma n, and this is corresponds to X equal to this is the representation. So I denote it by gamma. Now what do we have? I can take Tx and go for its representation. So there is some column vector here. Once again I repeat the same sort of analysis. What do I get? I get another B. So B, let me denote it by Bij, an n by n matrix such that if this is equal to B gamma. So B gamma is the image of Tx under phi b prime. So phi b prime maps this. So let me just do all these things and just put it across all these ideas. So what I have is I write x. Then you have phi b. I get a copy of r. So I get x represented by alpha. And then I have also have what is called phi b prime mapping Rn, and what I have is the corresponding gamma belonging to Rn corresponds. Okay, x is identified with the gamma, x is identified with the alpha. Now what do I have for that? So I have x is mapped to alpha is mapped to A alpha. Gamma is mapped to B gamma. Okay, so x belonging to x. This is in Rn. This belongs to Rn. Now our question is the following. You know that obviously B is T phi B prime. Okay. So how A and B are related? That's the question. Okay. This can be easily resolved. You will solve it. Okay, it's easy. You look at this figure and then you get it easily. What do I have? I want to get B. I want to say what B is. Okay. What is B? I go from gamma backwards to x and from x to alpha. From alpha to A alpha I go, and then from A alpha to Px I go backwards, and then from there I go to B gamma. So this path is traversed in a very sort of longish way by bringing in A also into the picture. So what do I have? Let me just mark it. So I write B gamma. This I write as, first I take gamma to x. So what do I get? I get phi b prime inverse of gamma. Phi b prime inverse exists because phi b is an isomorphism, therefore phi b prime is also an isomorphism from Rn to x. So I have this, right? Then what do? I have T here. So T, I apply T to. So I have reached here. So instead of t, what I do is I want to connect it to a. So what I do is from x I go to alpha. So what do? I apply. If I apply phi b to this, see I get x here. So this is x, and this is I reach alpha. Now what do? I have a. Apply a. So where do I reach? I reach here a alpha. That means I this. So from a alpha, what I do is I apply phi b prime, phi b inverse. So I apply. What do I reach? I reach here at tx. Okay? And then what do? I apply phi b. Phi b. So what do we have? Eventually reach that is a systematic way in which you arrive at this. Okay? Start with a gamma, go to x, then go to alpha, go to a alpha, go to tx, go to beta. This is what it is. Okay? So what do we have? See, now look at this. Now this is true for every gamma belonging to therefore I can now write B equal to phi b prime inverse a b prime phi b inverse. This is the connection. Okay? Now let us explore these things. What about this one? See, what is phi b composition inverse? Let us explore that. Phi b prime inverse, so you are going from Rn through x to Rn. Okay? So this is a map from R. Right? This is represented by, hence, the is A matrix C representation shows. Okay. See, all this discussion in Rn you can work in the standard basis. Okay. So this is with respect to the standard basis. I mean, all these matrix representations are with respect to the standard basis. Therefore, this is C. So I denote phi b composition, phi b prime inverse, that is this part, by C. What about this? This you can see is phi b inverse. Phi b inverse is from Rn to R. Okay, and what is that? The connection between the two is that this is you see that phi b inverse, phi b prime composition inverse is the inverse of phi b composition inverse. That's easy to work out. Work out the inverse. Okay, that's quite easy too. When you take the inverse, the order changes. Okay, so this is equal to phi b prime inverse composition inverse. But phi b prime inverse is phi b prime. So what is this? See, this is actually, this is actually C inverse. See, this one is C inverse. So this. So I can write this as, where have I written this as C equal to this. So what do I have? I have B equal to C inverse A C, where C is an invertible invariant matrix. Which corresponds to the change of basis and it is obtained through this one, this map. Okay. Affected by the map phi b composition B prime inverse. This is inverse. Okay, that is Now you observe that as we have seen, ID composition B triangle inverse is a map from and its matrix representation with respect to the standard basis is given into etc. En is given by this. So this is what you get. Okay. Therefore, you see that it is connected through an invertible matrix to a change of base. So I have BA. So A and B cannot be arbitrary. They are related through a invertible linear transformation or an invertible matrix. Okay. So A and B are of coordinate system. Coordinate system. So this observation is used. So we have explored this completely. Now let us ask a few questions. So on one side you have index. On one side you have index. On the other side you have got M cross N, that is all N by N matrices in R. Okay. Now you see that if you have a T is mapped to some A belonging to this, and this is affected by A affected through a sort of map between Ri to R. Right? Now you see that this mapping is not a unique map. Depends on this the image of A, image of T in isomorphism we choose from X to so if you use a different isomorphism, you get a different image. Okay, so this is what you have. now ask the question. Now this is the question I asked. So T is an abstract operator. Linear operator. So what I have is a So what I have here is you have Lx on one side, M n cross n R on the other side. Now T is an element here. T is mapped to some T. So also if I choose a different basis, T gets mapped to B. So T has several images. So what question you ask? The question you ask is the following. So this is affected through a isomorphism between X and R. Okay. And this is affected through an isomorphism of X and R. A second isomorphism from X and R. Okay. So this is what you want. Okay. Let us now start asking the following question. So first a wild question. Is it possible find a basis an ordered basis such that T with respect to that basis is equal to Q. It's a wild question. In short, what you are asking is this. You have a T here, that is fixed. Take any A. Can you find an ordered basis here such that the matrix representation of T is equal to A? Okay. If that is possible, then you see that every matrix represents every linear transformation. But that is too much to ask. You see that this is not possible. Why? Because if we take equal to I, is an ordered basis for X, then the representation of for the identity matrix I is the identity matrix. In fact, you see that for any choice of the ordered basis, the identity map is represented by the identity matrix. This is the important thing. Okay? So, you see that identity operator cannot be represented by an arbitrary matrix. Okay? This in turn implies identity operator cannot be represented by an arbitrarily chosen A. Has only one representation. Matrix, namely the identity matrix. So our question is answered in the negative. Okay. So this is not true. Okay. Right? Similarly, zero operator zero of x equal to is represented by the zero matrix in the with respect to any ordered basis, any choice of an ordered basis. So our general question falls true. So there does not exist it is not possible to find a suitable basis connecting given P with an arbitrary So what we ask now is this. However, we see that some is also the D may have a representation A and a representation B, and we also worked out the connection between them. Okay. So we ask, so our question is, now if P is connected, is represented by A as well as B in two different bases, how A and B are connected. It's very simple. We have seen that, already seen that in such a case B is equal to C inverse AC for some invertible C belongs to R. This is the connection. So if two matrices represent the same linear transformation, two different bases, then they are certainly connected. Okay, they are connected through a transformation. Yes, we have an invertible n by n matrix which relates B with A. Okay, that means the two different avatars of the same linear transformation are not arbitrary. Okay, one is related to the other. So if you have several avatars of the same linear transformation, then they are all related through a transformations of this kind. And remember, C is not the same in all cases. What I mean to say is that if B1 is related to A, A1, or if B1 is related to A, B2 is also related to A, then the connecting C is going to be different. Okay? So that is something to be observed. Therefore, now we ask a more structural question. So if you take M, n cross n R, we observe that some of the matrices are connected, some of them are not connected. Okay? So we define a relation. So on we define a relation. A is related to B if there exists A and inverted is B. That's that. This is it. If such a C does not exist, then A and B are not related. For instance, the identity matrix is never related to any other matrix. The zero matrix is not related to any other matrix. Okay, so these are some of the observations that we do. But A and B may be related, they represent the same linear transformation in different, with respect to different bases. In that case, there is a C that connects. Okay, so that's a relation that you can define on Mn cross n. So we have this relation. Now you see that one thing that you observe is that this relation, this is an equivalence relation. I leave the proof to you. First you verify that A is related to A. All that you need is use C as identity matrix. Now A is related to B, then B is related to A. That's the one statement. This is reflexivity. The second one is symmetry. The third one is A is related to B, B is related to D, implies A is related to B. That's, I leave it you to explore the proof of that. That's very simple. Here you use C as the identity matrix. Here you have a C determined immediately because of this relation. C inverse work as the relation to connect B with A. Then here you have a C1 connecting this, a C2 connecting this, and then a product of either C1, C2 or C2, C1, you can easily work out, connects A to B. Okay, so that's just a remark. You work out the details. We are not really. The third statement, I don't know. It's either CD or something that connected to with the C1 and C2 that connects A with B. Yeah, that is easy to work out. So what you have is now an equivalence relation. What does an equivalence relation do? An equivalence relation partitions the set. So M and N are, so this induces a partition on sorry. So what do you have? You have now blocks. So here, if you take two elements A1 and A2, then A1 is related to A2. If you take a B1 here, then A1 is not related to B1. Not related to B1. Okay, so that's simple. So all the matrices here are related to one another. All the matrices here are related to one another. All these are related to one another. Therefore, what happens? You see, you have on one side, you have X. On the other side, you have now you have got the equivalence classes. Suppose you take a T here. Suppose A is T is related to A. Through some choice of ordered basis for X. Then you see that any other element of this block, the block to which A contains. Now I can write this way. I can put A, let A be different. Is the all yeah the alpha of A prime is or A prime, where A prime is related to okay. So you see that T is represented by any matrix in the block once the matrix for T is equal to A. Okay. So that is the relation. Right? So you see that there is this equivalence classes. After making the equivalence classes, you can put boxes of this. So you look at the all elements of M, N cross N are partitioned through this. Now each partition block corresponds to an abstract linear transformation. Okay? So every element of the block A is so what we have is very much like the Hindu gods. God is manifesting in different forms. The T gets manifested in different through different matrices. That is, T gets manifested through different which are related to this thing. Most fascinating. It's also an awkward situation. An awkward situation in the sense that, see, you are happy if T is identified with exactly one matrix. But if not, you are uncomfortable. Okay? Therefore, if T is identified with two different matrices, then as I said, you are fairly uncomfortable in that situation, but you know they are related to one another. So we want to turn around this disadvantage into an advantage. Okay, so you know this is a visible disadvantage. Which one to choose? Okay, so you would like to choose a matrix which is probably the simplest representative of for T. Okay, so this is certainly a disadvantage, a source of discomfort. Because of non-uniqueness. However, we try to make the best out of this situation. By using a matrix representation as simple as possible for computations. In this context, what happens is that which matrix is the simplest? Because in matrices there are two operations, namely addition and multiplication. So the two operations that you do. Okay. So for computational purpose, which is the best out of it? In this context, we observe that a diagonal matrix ideal choice for computations. For suppose Only diagonal entries are non-zero, all others are 0. And one you can observe that lambda to the power k equal to, with respect to the same ordered basis, it is going to be lambda 1 to the power k very easily computed. So also P A equal to P lambda 1 for any polynomial with real coefficients. Polynomial with real coefficients. Okay, that is okay. We have P if equals to P naught plus then so you see, so there is a very definite advantage, and one knows how complicated it is to multiply. Is matrices even if n is so you see that that's the advantage of diagonalizing. So that leads to the next question. So the central question is, define any matrix A, is it possible to obtain a diagonal avatar of that's a question. Okay, so this is one direction in which investigations are carried through, which leads to the structural study of the original linear transformation that we started with, and then we call that diagonalizability. And the answer to this is this. This is the answer to this is this. It's not answer. So in general, the answer to this is this. In fact, you see that all symmetric matrices are diagonalizable. Even all normal matrices are diagonalizable. The normal matrices are, see, you have A, then you have the adjoint A star, Well, I don't want to go to the details of all this. Then if A star equal to A star A, then you say A is normal. So if A is normal, then it is diagonalizable. And in fact, the self-adjoint matrices, or what we call symmetric matrices in this context, because we are working with the field R, are a special case of that. Okay? So that's a different direction in this. So certainly there are matrices which are not diagonalizable. In fact, one can simply see that in the R2. The matrix A, B, 1, 0. Is not that means there does not exist a diagonal matrix which is equivalent to this. Okay, so I don't want to go into that question. Maybe in another series of lectures which I intend to give later on linear algebra, the entire course, an entire course on linear algebra, I will be dealing with this question. In fact, that is one of the central problems that you come across in linear algebra. Okay, so we will work it out later, but for the time being, I think this is enough on this question. Okay, so where do we go from here? That's what we should also think of. So what we observe is that we have matrix representations of a linear transformation. Therefore, it is easy to work out. See, the advantage of this isomorphism that you have this isomorphism that you have is that the lot of information about T can be obtained by studying the matrix for T. Matrix for T looked upon as a linear transformation from Rn to Rn. So in fact, it is by looking at the mirror. So this is a mirror image that you have. In that you see this, and you choose the particular mirror by choosing the right kind of isomorphism. So a lot of information that you get on the matrices, because we know a lot about matrices. So the results that are already available, all matrices can be reinterpreted for the operator T. That's the advantage. That's why you go for all this exercise. But this is the beautiful inner structure that you have, and which is worth exploring. But I will do that later. But for the time being, I think we need only know this. I think I just stretched it probably a little longer than what is required now. Okay. So now what I want to do is to introduce the Euclidean structure for Rn. So far we had only the linear space structure, which is an algebraic structure. Now I bring in a natural concept of length in Rn, and then it endows Rn with the Euclidean. Now once you have that, the concept of distance, natural distance between two elements of Rn, you are in a position to do analysis. You are in a position to talk about functions from Rn to Rm, then also talk about continuous functions, and then we want to go beyond that and ask questions like differentiability and so on. This is our major objective. So this part of the analysis I stop here and postpone it for some lectures on linear algebra. Thank you very much. Oh, yeah. We can stop here.